All right, we are off to our third objective. Actually, it's like 2.2 or 2b, and we're still doing quadric surfaces. This time, we're going to take a look at the equivalent of a parabola. So, in conic sections in 2 dimensions, a parabola is, those shapes that has a focus, directrix, and stuff like that. But we know the general shape of a parabola. Now, in 3 dimensions, the idea of a parabola will challenge us a little bit because we're going to have two types of paraboloids. So in our 3D analog of a parabola, we have a paraboloid, and there'll be two types of paraboloid that we'll see. All right, let's get to it. So our quadric surface, labeled as paraboloid, is going to be given by this equation. So the important thing to notice is that one of the variables is not being squared, while the other two are being squared. So that would be a good indication of your shape being a paraboloid. Now, the cross-sectional cuts that we're going to look at is letting the variable that's not squared, in this case the z, by letting that equal to 0 and then equal to some other constants, positive and negative constants, if they work. And by letting those equal to constants, we're going to get cross sections that would either look like an ellipse or a hyperbola. And so we break that down into two types of paraboloids. So the shape that we get when we let z equal to just a number, a constant, then we have some constant equals to something within a squared and b squared. So that's kind of like if a and b are both positive, then we have what we call an ellipse. And if you have cross sections that are ellipses, you have what's called elliptical paraboloids. Okay? Now, if the sign for b or a was a negative, so a and b have different signs, then the cross-sectional cut, when we let z equal to a constant, the cross-sectional cuts will look like a hyperbola. So then our paraboloid will have cross-sectional cuts that are hyperbolas, and so we will call that a hyperbolic paraboloid. So again, with the grammar, the noun here is the paraboloid, so that's the general shape. So paraboloid, paraboloid. And then we're going to use the adjective to describe what the cross-sectional cuts look like. So if the cross-sectional cuts look like ellipse, then we'll call it an elliptical paraboloid. If the cross-sectional cuts are hyperbolas, we will call it hyperbolic paraboloids. So our adjective will essentially describe what cross-sectional cuts we have. And when we look at our example of a hyperbolic paraboloid, you'll see why it's called a saddle. All right, another note here, and this goes for the other conic sections that we're going to study. If you switch the z variable with another variable like x and y, then the orientation of these paraboloids will change. Okay. For the ellipsoid, we don't really look at the orientation because regardless of how you look at it, it's still going to be an ellipsoid, so no big deal there. But for paraboloids and the other stuff that we're going to study, the orientation may change. Okay, let's take a look at this one. This one already has an orientation change, so let's take a look. If I were to write this so that y was by itself, I can see that this isn't that big of a deal either, but we'll take a look at solving for y by itself. Y is equal to x squared over 49 plus z squared over 7. So, okay, so whatever this is going to look like, it looks like it's just going to be a bunch of ellipses, right? Let's let y equal to 0, for example, equal to 0. Then we will have x squared over 49 plus z squared over 7 equal to 0. That isn't really getting much for us, right? So this looks like it's just going to be a dot. So this is what happens when y is equal to 0, y is equal to 0 on the xz plane, and we get a dot. Let's do something kind of that's not going to work, and let's let y equal to -1. You get x squared over 49 plus z squared over 7 is equal to -1, and that's not going to work because x squared plus y squared will be guaranteed positive, and you have a negative number there, so we'll cross this out, saying it's not going to exist on the negative y-axis. Let's do y is equal to 1 for another trace. I got x squared over 49 plus z squared over 7 is equal to +1. Now we have an ellipse. This crosses the x-axis at 7, I think, and I think the square root of 7 was like 2.65, so that's over here. So we have ellipsis for that. And then we can have this grow a little bit more, and we'll see that it's going to be ellipses that are getting larger and larger. So I would imagine this, and trying to draw this in 3 dimensions, you have your x, y, and z, and then when y is equal to 0, that's just the xz plane. We have a dot. We have a dot, and then when when y is equal to +1 on the parallel to the xz plane, so this is +1 here, parallel to the xz plane, we're going to get an ellipse. So we can imagine this, and then we'll get more and more ellipses that are going to get larger and larger. So we can imagine this is your paraboloid opening towards the positive y-axis. Okay, so it's called a paraboloid because of the general form of the equation, and the general shape would look like this. It looks like a parabola that's opening sideways, except it's 3-dimensional, so we have these ellipses as they shape the paraboloid. So that's called an elliptical paraboloid. Let's take a look at this example. We have z is equal to x squared minus y squared, and so the orientation is going to go up and down along the z-axis. And let's take a look at some traces. Let's draw the x, y plane for now, because we're going to let z equal to a bunch of things. Let's let z equal to 0 for starters. We have 0 is equal to x squared minus y squared. Now that's kind of a weird equation, and it looks like 0 would definitely work, but there are other values that would work. In fact, if we solve for like x squared is equal to y squared, and then we take the square root, and when we take the square root, we tend to look at the plus and minus of things. So I think the solution will end up being plus and minus y is equal to plus and minus x, so those are just diagonal lines. Now we'll see this a little bit clearer when we take a look at our example. Now if we let z equal to a different value, let's say z is equal to +1, we have 1 is equal to x squared minus y squared. So this is a hyperbola, if you remember, and this is a hyperbola that passes through and opens sideways along the x-axis, and it would have asymptotes of y is equal to plus and minus x, so it'll be opening sideways like this. Okay, if we let z equal to negative 1, we're going to get negative 1 is equal to x squared minus y squared. But the general form of the hyperbola, you want the constant to be positive 1, so let's multiply by negative 1 on both sides. You're going to get y squared minus x squared is equal to positive 1. This time your hyperbola should be going up and down, so that gets a lot more confusing. And if we continue on the path of putting positive numbers in for z, we're going to continue to have these sideways parabolas. Let's do that in the same color. And then if you continue to put negative values for z, we're going to continue to create these parabolas or hyperbolas going up and down. So trying to draw this would be quite difficult, unless you're an artist, which I'm not. But if we draw this first trace, that would be like a trace that goes through this way on the xy plane. Now as we draw, as we go positive, as we let our z go positive, you're going up along the x-axis here, or up along the z-axis, and you're going to be opening towards the x-axis. And then as you get higher and higher, you have these things that go higher and higher. And then down below the xy plane, you would get these hyperbolas that are going down there. So again, it looks not very surface-like shape, but let's take a look at our Calc-Plot3D. So here is the shape of the graph that we're looking at, and let's take a look at how that graph looks like. Alright, so you can see now why it's also called a saddle. So the things that I was trying to show you, the cross sections are happening when z equal to some specific values. So when z is equal to 1 or 0, we started off with, we look at this from the top, from the two-dimensional perspective, and we see the cross section over here as just an x. And as we let z get larger and larger, like positive 1, positive 2, I guess I'll zoom out a little bit, we see these hyperbola shapes from the two-dimensional perspective. Now let's put in the negative 1. We still see that the positive part over there, but the negative will start giving this shape that's hyperbolas that are opening up and down. Put negative 2. So if we go back to our three-dimensional look at this, if we look at this from the top without restricting our view too much, I think this plane has too many grid lines, so I'm going to cut it down to 10 so that it might render a little bit quicker. Let's have this view from the top and looking at the x going to the right and the y going up and down. That's close enough. You see the intersection is actually this this shape of a hyperbola that's going up and down. Okay. Another thing to note is that you can see parabolas in here. So I'm going to take this out, take the plane out, and just look at the shape of this hyperbolic paraboloid and show where some of these hyperbolas continue to exist. Maybe I'll take out the edges and then just take a quick snapshot of this and send it to our notes. Whoops. So instead of looking at our rough drawing, let's take a look at this point of view. It looks a little bit neater. If we go back to the shape, I should have kept the wires there, but if we go back to the shape of these things, you can see there's a bunch of parabolas that are going up and down if we look at it from one perspective. And then from another perspective, there's a bunch of parabolas that are opening downward. So we have parabolas opening upward and parabolas opening downward. Let's put the edges, the wires back on. You can see these parabolas that are opening up and down once I get it to the right orientation. You can see the parabolas going up and down, or opening upward, and parabolas opening downward in different points of views. And that you can see that by doing some more traces. Here is our original function again. Z is equal to x squared minus y squared. And when you let z equal to different values now, like I'm sorry, not z, but when you let like y equal to 0, you're going to get z is equal to x squared. When you let y equal to 1, you get z is equal to x squared minus 1, etc. And so these are parabolas that are opening upward. So you can see those upward parabolas over here. Now, when you let x equal to 0, you're going to get z is equal to negative y squared. When you let x equal to 1, you're going to get z is equal to 1 minus y squared. So all these now would be parabolas going downward. And then you can see the different shapes of those parabolas going downward. Alright, so these are our two types of paraboloids. We got elliptical paraboloids, which is what a regular paraboloid shape would look like. You would imagine that is a generalization of a parabola. But now, when your cross sections are hyperbolas, you have a hyperbolic paraboloid, which, as we saw, was in the shape of a saddle. Okay. All right, I hope that helps. Good luck.